Hello everyone, welcome to organolysis. So this is our conceptual problem solving part, and this is Sharpless Asymmetric Epoxidation Part-II. Okay, now in the previous video we were learned about all the mechanistic aspect of Sharpless Asymmetric Epoxidation and which type of reagents are used, what type of compounds that generally reacts to this type of Sharpless Asymmetric Epoxidation. We are already discussed in the previous video. Now in this video we are going to learning about some different aspects of the Sharpless Asymmetric Epoxidation, different kinds of examples, or previous year some questions. Okay, now let's start. Now at first we are taking the compound like this. This is a one kind of cyclic allylic alcohol. Now we already said in the previous video that this type of Sharpless Asymmetric Epoxidation generally takes place in the allylic alcohol. Okay, so you should have the allylic alcohol to form an epoxide. Okay, so this is our allylic alcohol. In the reagent that is used, TBU, that is tertiary tert butyl hydroperoxide, and titanium isopropoxide, and the plastate, the reagent which is used, the chiral ligand. This is okay, so this is our oxidant. We all know this is our oxidant, this is our catalyst, this is the date is our chiral ligand. Okay, so and this is used generally. So this is used generally, and the reagent that is moved for more angstrom of molecular shifts, that is we already discussed what is the importance of this molecular shifts, and the CH2 dichloromethane, that is the solvent ECM, and the temperature is quite lower to ensure the high amount of the product. Okay, so now we know that in case of plus DET we get the epoxy alcohol that is in the lower side, that is in the wedge form. So that is how we get this type of product. Now when we use the same substrate, when we use this type of minus DET, then we get the product that is in the upside, the epoxide which is in the upside. Okay, so this is in wedge form and this is in dash form. Okay, so now we get the different types of product like here. Now here we are taking a compound that is this is our E alkene and this is our Z alkene. Now when we take the two compounds, that is E alkene and Z alkene, but the reagent which is completely same for these two E and Z isomer, but we are getting the same product, that is the oxygen epoxide formation that is in the back side in the dash position. Okay, so we know that this type of bond is called wedge, and this is our dash bond. Okay, now this is how we can get this type of product. This is also the plastate is used, that is why we can get this lower side epoxy alcohol. Okay, so substrate generally used for this reaction is allylic alcohol. Okay, now if we have a compound like this, so it is very much important, and this example tells us that this reaction is very much stereoselective as well as regioselective. Just because of if you look at the compound, that you are getting two types of double bond over here. Now this is your allylic alcohol, and here is your alcohol which is in Z isomer for Z formation. Okay, Z isomer formation. Now if we use this type of this is oxygen, this is your catalyst, and the DIPT. Okay, now so what is DIPT? Now DIPT is the diisopropyl tartarate. Okay, so this is the DIPT. This is your DIPT. Now what is the structure of this DIPT? This is nothing but this is your OH. This is all similar with the plus DET or minus DET, and the rest part is this one. This is only change in case of D, only this. Okay, so this is your isopropyl group, that is why it is called diisopropyl tartrate. Okay, so this is your reagent. When we use this minus DIPT or minus DET, then you get this epoxy alcohol in the stereoselectively in the upside, and that is why this reaction tells us that this is very much stereoselective, just because of we get the you are getting these double bonds only, not this one. So this double bond will not react, it will unreacted in the product, and this epoxy, this allylic alcohol is stereo selectively form an epoxide. Okay, so this reaction is very much important for the Sharpless asymmetric epoxidation. Okay, now let's take the compound, the two important compounds, that is this two substrate is given over here. This is in S configuration, this center actually, this is your chiral center, that is why this is your S configuration, and this is your R configuration. Okay, now for this, the reagent that is used for this reaction is this is your our oxidant, and the reagent that is titanium isopropoxide, and this is plus DIPT is used. Okay, so plus DIPT, and then or the temperatures are the molecular shapes are said. Okay, now see the difference between them when we use the same compound, the same reagent, that is tertiary butane over here and over the same, all things are same for this S configuration. This allylic secondary, this is a secondary allylic alcohol, so this is R configuration, this is your S configuration. Now when we used this type of compound, we are getting two different types of product, that is this product is getting 98% and this is in lower amount of 2%. But when we, and this is also a fast process. Okay, so this is very much fast, this is comparatively much more slower. Okay, I will show you, I will explain you how why this type of why this is fast and why this is slow. And when we use this type of compound, the same reagent, we are getting this product in 62% and this is in 38%. Okay, now see the important thing is that this is the S isomer is reacted 100 times faster than this R isomer. Now why this is so? Now why this is so? Now I will show you here that we know that when we are placing this type of, we are predicting this type of the whether it is in the above side, whether it is in downside, we are getting this CH2OH group or this allylic alcohol part is in your lower right. Okay, now I also make it in lower right, and this is in the first condition, this is our R group, that is this one. Now I am written over here is R, and this is our hydrogen. Okay, now see the important part is for this reaction is when we use this plus tartarate. Now we are in both case we are using the plus tartarate one. So when we use plus tartarate, the reaction goes the oxidation or epoxidation takes place in this lower side, or when we use the D tartarate or minus DIPT, when we use this is in the upside. Okay, so when we use the upside, it is quite slower, and this side is quite much more faster. And why this is so? Now see, when the epoxidation takes place from the lower side, it will face this hydrogen only, which is in lower side. But when this epoxide, this chiral ligand will takes up and this epoxidation will form in the upside, it will face this type of bulky ligand. So that is why there is a steric repulsion, and that is why the lower phase attack is much more favorable, and it is comparatively faster. It is 100 times faster this from other one. That is R1. Now when we use the same thing, this is your R, this is your CH, this is your alcohol, and when this is in upside and is in your lower side is in R, then when we use this plus or tartarate, okay, so when we use this plus tartarate and when we use the two condition, that is our minus DIPT or any kind of tartarate. Okay, now in this case, which one will be faster? This side is very much faster, just because of this. When this epoxidation takes place from the upside, it will only face this hydrogen, so there will not so much steric repulsion. But when this type of plus tartarate will takes up this epoxidation form this epoxidation in the lower side, it will face this type of bulky ligand. So that is why this is your very much slower process. So R isomer is very much faster comparatively this S isomer. See, S isomer is very much faster compared to the R isomer. Now okay, now see the product, that is the plus DIPT. We all know that this epoxidation will take place in the dash position. So this will form in dash position, and there is a slower amount of formation of this this above alcohol, that is above epoxy alcohol. Now, but this is in very much in higher amount, that is in 98%. But when we use this same compound, but it is in R, that is this bulky group is in the back side, then this amount product ratio is different. Product ratio are very much different. That is, this is formed in 62 amount, but this just because of this, although this is in slow step, but this will try to from this lower side of alcohol, lower side of epoxide. That is why it is in 62. But this forms this try to, although it is trying to form this lower side epoxide formation, but it also get we also get this type of over, that is epoxide from the above side. Okay, so this is also formed in the 38%. Okay, so this is the difference between this AL isomer and S isomer and R isomer, and that is how we can distinguish both of them and the percentage of this product. Okay, now next the question comes, and the question which was came in CSIR-NET June 2015. Okay, this is also a very much important question. Okay, so there is an important terms arises, that is a kinetic resolution. Okay, so that is our kinetic resolution. Okay, what is kinetic resolution? So for this we know this is our secondary alcohol. Now this alcohol has two different types of now what is for okay, for after going to this, before going to this question, now we have to know this kinetic resolution. The kinetic resolution is basically the to differentiate between two isomer which is in the racemic mixture. Okay, so we all know what is racemic mixture. There is a two product, that is Fe, R and S, they both are in one process, that is called the racemic mixture. Now in case of kinetic resolution, two isomers react with two different types of rates. Okay, so rate of the reaction will be different. So with in case of the chiral ligand when we use, so that is why this term kinetic resolution arises, to differentiate the enantiomer between when we use a reaction in the racemic mixture, when the substrate which is used, that is in racemic mixture. Okay, so this oxygen, I will show you, it will be clear when we discuss the example. Okay, now this secondary alcohol has a two possibility of two side, that is either this OH is in upside, or either top side, or either OH group is in bottom side. So there will be two different types of isomer will be possible. That is, I have not written the overall part. There is a possibility of this group or the rest part, and there is a possibility of this one. Okay, so when we are going to use, that is minus DIPT. Okay, so when we use this minus DIPT, we all know that this above sided top sided epoxidation will take place, but the top side epoxidation will not take place, will also take place, but in case of this OH form with this OH. Okay, so when we use this this type of OH which is in upside, we are getting this product like I'm written over here, we are getting this product. Okay, so this will be and this is very, and other rest parts also there, and this is we are getting, this is in 96% enantiomeric, so that is very much higher yield we are getting. Okay, but in this is comparatively not reactive as compared to this one. Okay, now that is why when we use minus DIPT, we are getting this type of compound. Okay, now this OH is in upsided, so that is why this minus DIPT will not deliver this oxygen to the upside. So then it will form to then it will try to donate this epoxy to form this epoxidation in the lower side. Okay, so that is why we are getting this type of product, two different types of product. Okay, so this isomer is, this enantiomer is not so much reactive that as compared to this one. Okay, now let's come to the next question, and the last question, which is very much important for your exam, and which question also came in CSIR-NET June 2017. And the question involves two different types of product, that is where the major product A and B are forming their sequence, given a substrate, that is allylic alcohol. You have given the plus dt, that is our Sharpless epoxidation part. Now from this you have to identify the structure B also, that is for this you have given tert-butyl SH, tert-butyl thiol and this NaOH. Now for this we all know that what will be our product. The plus DET is given. We all know this plus DET already, it generally delivers this oxygen to the lower side, so that is why we are getting. Now for this, from the structure A, we generally get our product. So this B is not our option, so this D also not our option. So either option A or option C will be our option, will be our correct answer. So we are getting this one, right? So this is our OH. Okay, now when we use the NaOH in this reaction mixture, then what will be our product? This OH minus generally takes a proton just because it is acidic, and this is our O minus. Now then we get, this is your O minus. Now this O minus directly goes over here, and this bond and this epoxide ring open up. So this type of rearrangement is called PAYNE rearrangement. Okay, I will show you how this negative charge directly attack to this center, and this epoxide is open up, and this and there is a formation also in epoxide. Now the question comes is that this is our O minus. Now question comes is that how this O minus is either in lower side or when the epoxide is formation over here, this center is either in lower side or downside, lower side or upside. We all know that this epoxide is in lower side, so this O minus did not attack to this lower side, so it will try to attack in the above side. So this epoxide, the formation of this epoxide is in upside. Okay, now we have the reaction mixture in the TBUSH, tertiary butyl thiol, and this hydrogen, this OH minus, takes a proton from here. This is your S minus. Now this TBUS directly attack to this center, and these bonds go over here. Okay, and this will take a proton, and that is how you can get, this is our OH, is TBU. Okay, so that is our overall PAYNE rearrangement. It is our PAYNE rearrangement. Okay, now see, you have to know two different types of name reaction, that is Sharpless Asymmetric Epoxidation and PAYNE rearrangement. Then you can understand, or then you can answer this overall question. Okay, now see the answer. This OH is in back side, and this is tertiary butyl group is in above side, so this is not our option. The remaining part, that is our option C, is that this OH is in upsided and this tertiary butyl group is in plane. Okay, so this is our overall Sharpless Asymmetric Epoxidation. I hope this video is very much helpful for you and very much informative also for you. And if you find this video very much useful, share it with your friends, and please subscribe to my channel, and please like to my video, and it motivates me to make more good videos. Okay, so that's it for this video. Thank you so much for watching.